Hello, Algebra 2 class. I wanted to make this screencast to simply summarize a little bit more succinctly what we went over today, Monday, April 19th, starting a very important unit. Rather, we didn't start this unit, but talking about a very important unit, which is trigonometry. We did this warm-up. We looked at which points on this circle here have the same distance from the x-axis, in other words, the same height. And this related to our work with Ferris wheels last week, which we also reviewed so that you could do your homework 10B more successfully. And that would be due by the new due date, which is this Thursday. Okay, this Thursday at 8 a.m. Then what we talked about was angles of rotation. All right, and we said that an angle is in standard position, an angle is in standard position when the initial ray lies on the positive x-axis and the terminal ray, which is the one that opens and rotates, is moving counterclockwise. All right, so we said that whatever angle that the terminal ray makes with the initial ray, where the vertex is, where these two rays meet, that angle is known as our angle of rotation, and you can see that on this diagram. The reference angle, however, which is always the one that you put in your calculator, is going to be the angle that your terminal ray makes with the x-axis, and you can see that on the left side here, over here. All right, now, we also talked about a few formulas to help us to be able to determine an angle of rotation and a reference angle. So if we take a look here at this example on the left, we see that our angle of rotation, the one in the red, is 210 degrees because the initial ray is here, the terminal ray is here, and so when we rotate that out, we're clearly going past 90 degrees, which is, oopsies, up here, past 180 degrees over here, and even further than 180 degrees, we're going out to 210 degrees. Now the reference angle, remember, we just said, is the angle that it's the angle that the terminal ray makes with the x-axis. All right, and this reference angle is also the angle of reference for the triangle that we've been dealing with and putting the trig ratios into our calculator for. So the reference angle in this case, which we called theta prime, is 30 degrees. Now let's go back. Actually, let me talk about a clockwise rotation. We said a counterclockwise rotation is a positive angle of rotation, and a clockwise rotation, I'm confusing myself again, is a negative angle of rotation. All right, so when we start with our initial ray here, but we don't move this way, no, we move this way, well then that is a negative angle of rotation. All right, and so here, if this is negative 90 degrees, clearly this terminal ray lies between 0 and negative 90 degrees, making this theta, our angle of rotation, 45 degrees. And guess what? When your angle of rotation is between 0 and 90, it's the same as your reference angle. So our reference angle is also 45 degrees. One key note is that our reference angle is always a positive acute angle. All right, so our reference angle is always a positive acute angle, and that's why we always put a positive angle into that calculator. Reference angle is always positive and acute. All right, hence this 30-degree reference angle here. This one, we said that our reference angle was 45 degrees, positive 45 degrees, even though the angle of rotation is negative. Now, we further looked at how to find, when we fixed up this chart here, how to find the reference angle based on the quadrant you're in, or the angle of rotation based on the quadrant you're in. Now, we just said, let me use this, oops, what happened? I don't know what you just saw, but whatever. The reference angle here is, all right, so when we're in quadrant 1, let's take a look here. Notice, our reference angle is going to be the same as our angle of rotation. So reference angle is denoted theta prime. It's going to be the same as theta, which is our angle of rotation. Now, once we move beyond 90 degrees, and let me write that down up here, this is clearly 90 degrees, this is 0 degrees, this is 180 degrees, that makes a straight line, this is 270 degrees, and if we complete this circle, 0 and 360 land in the same place. So once we move our terminal ray out beyond quadrant 1 and we land in quadrant 2, oops, I meant to do that in green. When we land in quadrant 2, well then, our theta, our angle of rotation, is clearly bigger. It's more than 90 degrees. And so, if we are given the angle of rotation, we can find the reference angle, which is this guy, theta prime, right here. Why? Because in quadrant 2, the angle of rotation falls just short of 180 degrees, right? It doesn't really make it down to that straight flat line. It falls short of 180 degrees by the size of the reference angle. So say, for example, we had theta equaling, our angle of rotation equaled 150 degrees. Well, we could find our reference angle using this formula. So we could take 180 degrees, say 180 minus theta prime being our reference angle, equals 150. Simply solve for theta prime and you're going to get that theta prime equals equals 30 degrees. Divide by -1 on both sides and we get 30 degrees. So that's an example of how to use that formula in quadrant 2. Now in quadrant 3 we have the same concept. It's just that our angle of rotation has now gone beyond 180 degrees. So that means if our angle of rotation goes even further than 180 degrees, well, then clearly the angle of rotation is going to be greater than 180 degrees, and it's going to be greater than 180 degrees by the amount of the reference angle. All right, so here in this case, this is theta, this is our angle of rotation. Our reference angle is always the positive acute angle made by connecting the terminal ray with the x-axis. And so this is our reference angle right here. And so let's say that this theta was 220 degrees, right? Let's say that that was 220 degrees. All right, well then we can use this formula, except now instead of subtracting the reference angle, we actually add the reference angle to it because we're going more than 180 degrees of rotation. So if we're given our theta, we need to find our reference angle. Well, once again, just solve for that reference angle. We're going to get theta prime reference angle is 40 degrees. And so that means right there, theta prime is 40 degrees. And so that would be the angle that you use to find the tangent, the sine, the cosine, whatever you're looking for. Now let me erase what's on the screen here and talk about our last quadrant, the fourth quadrant here, and say that when we are dealing with the fourth quadrant, an angle of rotation that lands in the fourth quadrant, the terminal ray lands in the fourth quadrant, let me be more precise. Well, take a look. It's falling just short of 360 degrees. And so since it's falling just short of 360 degrees, we can use 360 degrees in our formula. So let's say, for example, we have this angle of rotation. Now we know right here this is 270 degrees, so it's clearly an angle between 270 and 360. Let me call it a 300 degree angle. Well, if this theta equals 300, then we can find our reference angle, boop, theta prime, by using this formula. So we can say 360 degrees minus theta prime equals our angle of rotation, which is 300 in this case. And we're going to find that our angle of rotation, our reference angle, equals 60 degrees. And so that is the number that we would put in our calculator when calculating our trig ratios, sine, cosine, tangent, whatever you're doing. All right. Now lastly, let's go over page 24 a little bit more clearly this time. All right, so page 24, this is similar to the homework that you're going to have tonight. We can see, based on the diagram in the top right, that angle theta is between 0 and 90 degrees. Okay, similar to a Ferris wheel, right? Now, we talked about the sine of theta in terms of a circle on a coordinate grid, and we said that the vertical distance is y, meaning our opposite angle, our opposite side is y, our adjacent side is x, and our hypotenuse is now known as r, which is the radius of the circle. Let me just label these here, x and y. So the sine of theta, and this could actually be considered theta prime, going back to the last page we were working on, because this is a reference angle as well as the angle of rotation. But let's just deal with the angle of rotation. The sine of this angle of rotation is going to be opposite over hypotenuse, so it's actually going to be y over r. Now, we're going to use this definition for any angle of rotation. The sine of theta always equals y over r, not just in quadrant 1. So, let's consider this point, negative 3, 4. Let's plot it here. Negative 3, 4. That's our point. And look, we're in quadrant 2. Okay, it's on this circle, x squared plus y squared equals 25. Remember, the formula of the circle we talked about last week is x squared plus y squared equals r squared. That means 25 equals r squared. Take the square root of both sides. R is 5. So what is the radius of this circle? It is clearly 5. This circle is going to be centered at the origin, and so let me sort of, it's not going to look very good. Let me just put a couple more points, equally spaced, and say that that's our circle. All right, now where is our angle of rotation? All right, so remember, our angle of rotation, this is our our initial ray, and coming up to this point that we have here is our terminal ray. The angle of rotation is the angle made there, and so this is theta. Now, for the angle of rotation that we just drew, what would be the value of sine if we use this definition that we developed earlier? Okay, well what we're going to say is that the sine of theta equals y over r. Okay, let me make a reference angle then, and a triangle from this point. Where did we have? From this point right here. So here we have a negative 3. Here we have a positive 4. And we know that our r, our hypotenuse, is 5. Okay, I'm actually going to make this positive, a positive 3. Because we know that our reference angle should be positive, and if I put any negative values in there, it's going to be it's going to throw off this calculation. So if sine of theta equals y over r, then sine of theta equals 4 over 5, which means that the arc sine of 4 over 5 equals theta. Pause, do this calculation in your calculator, and you'll see that theta equals 51.1 degrees approximately. However, we did not just find the angle of rotation. What we found was the reference angle. So if our reference angle is 51.1 degrees, then you can calculate the measure of